Polynomial functions. Polynomial functions. A polynomial function in one variable is a single term or the sum of two or more terms with variables having whole number exponents and real number coefficients. The standard form of a polynomial looks like f of x equals ax to the n plus bx to the n minus 1 plus ... plus cx plus d. So in other words, the values of a, b, c, d have to be real numbers, and the exponents, this n, n minus 1, have to be whole numbers, so 0, 1, 2, 3, 4. Standard form means that the highest power or exponent has to be first, and then we have descending exponent order as we move through each term. The degree of a polynomial is the greatest degree of any term in the polynomial. The term with the greatest degree is the leading term, and its coefficient is called the leading coefficient. The term with no variable is the constant term. So in this standard form of a polynomial, the value of d has no variable, so that is the constant term. So note that 0d would be the y-intercept. Recall, to find y-intercepts, you let x equal 0, so the only term that would be remaining is the constant term, in this case d. Let's go ahead and move on to an example. Here we have a standard form polynomial. F of x equals 3x to the fifth minus 4x squared plus x minus 2 is a polynomial with 4 terms. So terms are separated by that addition or subtraction. The degree is going to be 5, so that is the highest exponent out of all of the terms. The leading term is the term with the highest power or highest degree. So the leading term is 3x to the fifth. And the constant term is the term without a variable. So in this case, it's -2. It comes with the sign. As opposed to the function y equals 1 minus the square root of x, this is not a polynomial because it has an exponent of 1/2. And 1/2 is not a whole number. Recall that the square root of x would be x to the 1/2, and in order to have a polynomial, we need exponents that are whole numbers. In this example, we want to state the degree and write the polynomial in standard form. Then find the leading term and the constant term. In part A, we have f of x equals 5 minus pi x plus 1/3 x squared minus 2x to the fourth. So this is a polynomial. All of my exponents are whole numbers, and all of my coefficients, the numbers in front of variables here, are real numbers. The degree of this polynomial is going to be 4 because that is my largest exponent. Standard form of this polynomial is going to be rewriting so that each term is in descending power order. So standard form is going to be f of x equals -2x to the fourth plus 1/3 x squared minus pi x plus 5. The leading term, well, the leading term is the term with the degree with the highest exponent. So the leading term is -2x to the fourth. And the constant term, the one without a variable, is 5, +5. In part B, we have y equals -3x times the quantity 2x minus 1 squared. And first we want to go ahead and think about the degree. So let's go ahead and start to expand out this particular polynomial, since we'll have to write it in standard form anyways. So here we have -3x, and then the quantity 2x minus 1 squared is 2x minus 1 times 2x minus 1. Now here, if I think about 2x minus 1 times 2x minus 1, I can distribute all of that out. So I'd have that negative 3x in the front, I'd have 4x squared, and then outer and inner is going to be minus 2x, so minus 4x plus 1. But bottom line is that we would have 2x times 2x, well that's 4x squared, and then the other terms are of lesser degree, so we'd really only need to think about the 4x squared and that multiplied by the negative 3x in the front. So the degree is going to end up being a degree 3 polynomial. When I distribute in that negative 3x to each term, the highest power of x will be a 3. And we will finish distributing in the negative 3x because we do want standard form of this polynomial. So we're going to have negative 12x cubed plus 12x squared minus 3x. So that would be our standard form, writing our terms in descending power order. The leading term now we can see is negative 12x to the third, the term with the degree 3, so negative 12x to the third. And the constant term, well, the term that doesn't have any variables is just 0, because at the back here I could think about having a plus 0, so that would be my constant term. Now ideally we'd like to be able to find the degree and the leading term of a polynomial in this form, this factored form instead of standard form, without having to multiply it all out. So we'd want to be able to think about this as 2x and squared would be the highest power of x after multiplying out this 2x minus 1 quantity squared piece, and then if I multiply that by a negative 3x, that's going to give me a negative 12x cubed, making that degree 3. So that's eventually going to be kind of the goal, is we don't want to have to write it in standard form to identify the degree and the leading term. Now let's move on to talk about the graphs of polynomial functions. Polynomial functions of degree 2 or higher have graphs that are smooth, which means they have no corners or cusps, and they are continuous. And by continuous, we mean there's no holes, jumps, or breaks in the graph. So in this example, the question is, could the graph shown represent a polynomial function? If not, explain why. In our first graph, we have an absolute value function that's reflected over the x-axis and shifted left 2. So we have a corner to our function at negative 2. So this could not represent a polynomial function, so the answer is no. And the reason is because there is a corner at x equals negative 2. The second example here, we do have a smooth graph, so we don't have any corners or cusps, which are basically sharp turns. We have these nice smooth turns. And we are continuous, so I can draw this particular graph without ever lifting up my pencil. There's no holes, jumps, or breaks in the graph. So the answer here is yes, this could represent a polynomial function. Finally, this last example, I have these 3 pieces to my function, and they're separated by vertical asymptotes at negative 3 and at 2. So this could not represent a polynomial function. The answer here is no, and that's because I am discontinuous. So I am discontinuous at 2 different places actually, at x equals negative 3 and at x equals 2. Now we're going to look at a specific type of function called a power function. A power function is of the form f of x equals a times x to the n. So now we're going to look at some examples of power functions that are polynomials. So the function f of x equals x to the first power, well that's of the form ax to the n. I have 1x to the first power. That is a power function, which we know represents a line that passes through the origin with slope 1. So this is a linear function. We can also look at the power function f of x equals x squared, which we know is a parabola when we graph it, and we call this type of function a quadratic function. Moving on, we can think about the power function f of x equals x to the third. So f of x equals x to the third was one of our basic functions. We know that it is continuous and it lives in quadrants 1 and 3 and passes through the origin. And we call this power function a cubic function. Finally, we're going to go ahead and look at the two power functions f of x equals x to the fourth and f of x equals x to the fifth, and kind of establish some relationships between these power functions and the ones previous that have lesser powers. So f of x equals x to the fourth, that would be considered a quartic function. And its graph is similar to the graph of x squared. It still is a U shape, but it's a more flattened out U. So notice it also passes through the points 1, 1 and negative 1, 1, because if we plug in 1, 1 to the fourth is 1, negative 1 to the fourth is 1, just like x squared passes through 1, 1 and negative 1, 1. But the graph of x squared we call a parabola, and that's a very specific name for a quadratic function's graph. A quartic function just has a U shape, but it's not considered a parabola because it actually flattens out more in between that negative 1 and 1. So it's closer to the x-axis for more values between negative 1 and 1. And for the graph of x to the fifth, so that's a quintic function, and it's pretty similar to a cubic, a degree 3, in that it passes through 1, 1 and negative 1, negative 1, because again, if we substitute in those values into x to the fifth, those are the y values that will come out, just like x cubed. But it also is more flattened out between negative 1 and 1. And the reason for that flattening out as we increase the power is because essentially as we're plugging in fractions, those are the values that live between negative 1 and 1, so fractions like 1/2 or 3/4, if we raise those to a power like 5 or 4, it actually makes those numbers even smaller. So if I had something like 1/2 to the fifth, that's going to be 1 over 32, versus 1/2 to the third, that's 1 over 8. So 1 over 32 is much smaller, so that's why we have this flattening out happening the higher power that we have on these types of power functions. So the pattern I kind of want you to start to recognize is when I have an even degree on these power functions, they look pretty similar. They have this sort of U shape, but really what I want you to focus on is that both ends of the function are going towards positive infinity. Versus if I have an odd power degree function, so x to the 1, x to the third, x to the fifth, now the end behavior, so towards the right and the left side of each of these functions, they're going opposite. So instead of both going up, like x squared and x to the fourth, for all the odd power functions, one side's heading up and the other side is heading down. In fact, the right side's heading up and the left side is heading down. So that's just some patterns I want you to recognize as you observe these power functions. Just a quick note, we were looking at power functions that were polynomials because they have whole number exponents, but note that the square root of x, which is of course x to the 1/2, that would also be considered a power function. So would 1 over x squared, because we could rewrite that as x to the negative 2. So these are also power functions, but we specifically were thinking about power functions that are polynomials. In this review example, we're going to use transformations to graph y equals negative 1/2 times the quantity x plus 2 to the fourth minus 1. So the only part that's really new here is that our parent function is x to the fourth. So we're going to identify the parent function as x to the fourth, and let's identify the transformations. The negative in the front is going to reflect over the x-axis. The 1/2 that's multiplied in the front is going to give us a vertical compression by 1/2. And then finally, we have our translations. So plus 2 inside with the x is going to move us left 2, and minus 1 on the outside is going to move us down 1. So we have left 2 and down 1. So let's go ahead and apply these transformations then. So our parent function, we'll start by sketching our parent function. So it passes through 0, 0, 1, 1, negative 1, 1, as we said. And I'm going to go ahead and sketch it, and I'm going to emphasize that it really flattens out on the bottom there. So this is going to be my function x to the 4th. Now, if I want to do the vertical compression next, I'm going to affect the y value since I'm a vertical compression. So instead of 1, 1, this coordinate point would be 1, 1/2. So I'd have 1, 1/2, negative 1, 1/2. And then I would go ahead and sketch that. Kind of looks like it's running into each other a little bit. So this is 1/2 x to the 4th. It doesn't intersect, it kind of just looks like it does there. And then we're going to reflect it over the x-axis next. So our reflection over the x-axis, we're going to still pass through 0, 0. Now it won't be so cluttered. We're going to have 1, negative 1/2, negative 1, negative 1/2. And then again, I'm going to try to make it look like it flattens out more near the x-axis. And then we'll move everything left 2 and down 1. So we're going to go ahead and move our vertex negative 2 and then down 1. So negative 2, negative 1, and then we'll have our other coordinate points that are just a half unit away below it. And then we'll go ahead and connect those, again trying to make it look a little flatter on the bottom. So this is going to be our final graph here of y equals negative 1/2 x plus 2 to the 4th minus 1. And then we'll label this was negative 1/2 x to the 4th. So very similar to what we did with our other parent function. So now we're just trying to identify this new parent function x to the 4th, which is a little bit more flattened out. And we just want to do our best to emphasize how it really does flatten out more than the graph of x squared. So in our last example, we graphed a higher degree polynomial, a quartic polynomial, using shifts in the graph and transformations. But what if we have a higher degree polynomial in standard form? That whole ax to the n plus bx to the n minus 1, etc. How would we graph something that looks like that? Well, we're going to kind of break that apart into pieces. So we're going to start by determining what we call the end behavior for a polynomial function that looks like y equals ax to the n plus ... plus a bunch of terms. And we don't really care what those other terms are because we're going to determine this end behavior using the leading coefficient test. So the leading coefficient test is first going to have us think about the degree of the polynomial, whether the degree is even or odd. So if I have an even degree polynomial, so n in this case is even, then there's two possibilities at that point for the value of a being the leading coefficient. A could either be greater than 0, meaning a is positive, or a could be less than 0, meaning a is a negative value. So my tip for this is to think back to our familiar function y equals x squared. This is an even degree with a positive leading coefficient. The leading coefficient is 1. So if we want to describe its end behavior, well, the ends of x squared are both pointing up. So the right side is pointing up and the left side is pointing up. So those are the only parts we want to think about in terms of x squared are the ends, because we don't know what happens in the middle. So I'm kind of just going to put like a wavy dotted line because we don't know what happens in the middle. So in general, if I have an even degree with a positive leading coefficient, the left side and the right side point up. Now if I have a negative leading coefficient, then I would think about instead y equals negative x squared. And a negative in front of a function reflects over the x-axis, so both sides would be pointing down in terms of end behavior. The left side points down and the right side points down. And again, we don't know what happens in the middle. So to describe what is happening using an alternate notation, what we're saying is that as x values are going towards positive infinity, so positive infinity on the x-axis, f of x values, those are y values are going to positive infinity. And as x values are going towards negative infinity, what is happening to f of x? F of x is still going to positive infinity. And when I have a negative leading coefficient, as x goes to positive infinity, my y values, f of x, are going to negative infinity. And as x goes to negative infinity, my y values, my f of x values, are going down to negative infinity. The other possibility is if I have an odd degree leading term. So in other words, if n is odd. And then we have the two choices of a, the leading coefficient, to be positive or negative. So my tip here is to think about y equals x cubed, or really any odd degree power function that we are already familiar with. So we should be familiar with x cubed. And the end behavior is that the right side towards positive infinity points up. So as x goes to infinity, y values f of x goes to positive infinity. And the left side points down. So as x values go to negative infinity, the y values go towards negative infinity. And we don't really know what happens exactly in the middle. In general, we know what happens in the middle of x cubed. But for any odd degree polynomial with a positive leading coefficient, the right side points up and the left side points down. And if a, that leading coefficient, is negative, then of course we reflect it. So the left side points up and the right side points down. So as x goes to positive infinity, the y values go to negative infinity, f of x. And as f of x goes to, or as x, goes to negative infinity, f of x goes to positive infinity. So I like to think about it as if I have an odd degree, odd goes the opposite direction. So it's just a matter of the leading coefficient being positive, the right side goes up, the left side goes down. If the leading coefficient is negative, then the left side points up and the right side points down. But if it feels like a lot to memorize, always just go back to x squared and x cubed, because those are parent functions that we should already have memorized. In this example, we're going to use the leading coefficient test to determine the end behavior of the graph of the given polynomial function. Sketch it and describe it at the ends of the function. So here first we have f of x equals 10 minus x minus 5x to the fourth. So we'll start by identifying the leading term. The leading term tells us both the degree and the leading coefficient. So our degree is 4, which is even. So we know that either both sides point up or both sides point down. Well, the leading coefficient is negative 5. So since the leading coefficient is negative, both sides point down. So we can relate this, we can think about like negative x squared. So because it's even and I have a negative leading coefficient. So both sides are going to point down. So this is a sketch of the end behavior. And again, we don't know what happens in the middle. And to describe what happens as x goes to positive infinity, as x goes to the right, my y values go down to negative infinity. And as x values go towards negative infinity, again, my y values go down to negative infinity. In the next example, we're going to have to do a little bit more to think about the degree and the leading coefficient. I have negative 3x cubed times the quantity 2x minus 3 squared. So this is not in standard form. So in order to think about the degree, I'd have to think about what would happen if I multiplied it all out without actually multiplying it all out. So 2x minus 3 squared, well, that would end up being 4x squared, and then I'd have some other terms. But that 4x squared would be the highest term for that distribution, and when I think about multiplying 4x squared times negative 3x cubed, I'm going to end up with a degree 5 overall. So my degree is going to be a degree 5, and that's an odd power. And then my leading coefficient, well, that would end up being negative. I had 2 squared, that 2x squared, that was 4x squared. And then I have this negative 3. So my leading coefficient would actually be negative 12. So if I have an odd degree, odd means opposite, they point opposite directions, and a negative leading coefficient means that we would think about x cubed, but then flip it. So instead of the right side going up, the left side goes up and the right side goes down. And we don't know what happens in the middle. So that's a sketch. And now to describe it, well, as x goes to infinity, as I move to the right, my y values go down to negative infinity. And as x values go towards negative infinity to the left, my y values go up to positive infinity. And in our last example, we have f of x equals 3x squared times the quantity x plus 2 squared times the quantity x minus 1 squared. We definitely don't want to have to multiply all this out and write it in standard form to find the degree. We'd simply want to think about that each of these binomials, x plus 2, x minus 1, each squared, would give us an x squared and an x squared, and that would multiply to this 3x squared in front. So that would mean that the degree overall is going to be a degree 6. So x squared, x squared, x squared, all multiplied out would be x to the 6th, which is even. And then my leading coefficient this time would be just 3, because there was just 1's in front of each of these x's. So I have this 3 in front that would multiply to those 1's. So I have a positive leading coefficient. So we can basically just think about x squared, right, an even degree with a positive leading coefficient. So the right side points up and the left side points up. As x goes to both positive infinity and negative infinity, the y values, f of x, goes up to positive infinity. Now that we've covered the end behavior of the graph, we want to think about real zeros and their connection to the graph. So if I have a function, f, and r is a real number for which f of r equals 0, then r is called a real zero of f. Now we're going to talk about these zeros and what are called their multiplicities. So let's say we're given a polynomial, f of x equals a times the quantity x minus b to the n times the quantity x minus c to the m times the quantity x minus d to the k. Here this is a polynomial, but not in standard form. Well, since it's factored, x minus b as a quantity, quantity x minus c, and quantity x minus d are all called factors of f of x. And therefore b, c, and d are solutions to the equation f of x equals 0. Now, these solutions, b, c, and d, are again called real zeros. We just defined that above, but they are real zeros of multiplicities n, m, and k respectively. So b is a real zero from this factor, and because the power there is n, we say that b is a real zero of multiplicity n, c is a zero of multiplicity m, and d is a zero of multiplicity k. And any solution, any real number solution to the equation is an x-intercept. So b comma 0, c comma 0, d comma 0 are all x-intercepts of the graph of f of x. In this example, we want to form a polynomial function given the following information. Assume all zeros have multiplicity 1 unless otherwise stated. So we want to form a polynomial in part A with zeros, -2, 0, 1, and 4, but 4 has a multiplicity of 2. And this has to be a degree 5 polynomial. So what we're going to do is start out by saying f of x is equal to, well, if -2 is a 0, then x minus -2 is a factor. And we assume it's to the first power because all multiplicities are 1 unless otherwise stated. If 0 is a 0, then the factor x minus 0 has to be included in our polynomial. And again, with a multiplicity of 1. If 1 is a 0, then x minus 1, again, to the power of 1, has to be a factor. And then lastly, to have 4 as a factor with a multiplicity of 2, we need a factor that looks like x minus 4 as a quantity squared. And if I simplify this a little bit, or at least clean it up a little bit, I'm going to put that x minus 0 to the first in front, so that's just x. And then I'll put x plus 2 from x minus -2. Then the factor x minus 1, followed by the factor x minus 4 squared. So if we multiply this all out, which we won't, we don't have to, we can tell just by looking this is a degree 5 polynomial. I have x to the first, x to the first, x to the first, and here it would be x squared. So altogether I have x to the 5th would be my degree. And then in part B, we have to create a polynomial with zeros, -1, 1, and 3. So we just assume they're all multiplicity 1, and this polynomial needs to have degree 3 overall. So we're looking at f of x equals x, and then we'd have minus -1, so we want to be able to jump straight to x plus 1. And then our other factors will be x minus 1, and x minus 3 to ensure that we get the zeros of 1 and 3, all with multiplicity 1. And if we did multiply this all out, we would have a degree 3. We'd have x cubed if I went through the process of all the distribution.